Okay, this is the path of the presentation. Again, heat flow, geothermal energy, and bottom hole temperatures, and some things we know about it, and some things that do cause us problem. Then, when we get through all of this, I'm going to show you what we've discovered about the Williston Basin and how it is different from other basins. And we came up with some very surprising results that we think enable us to determine what the heat flow is just based on the uncorrected bottom hole temperatures and some information we have on the subsurface. Well, we know that if we want to have an economic geothermal system, we need to know a lot about the subsurface. The three basic things we need to know are the temperature, the depth to the resource, and the reservoir properties. And again, economics are the basic thing behind all of this. So where does heat flow come in? It's absolutely crucial for understanding what we're trying to do. And one way we can do this on a large scale is to make a map of an area that shows what the heat flow is. So, very critical thing. We've been attempting to do a lot of geothermal work in North Dakota, encouraging industry and so on to come in and work with us. We have had a lot of questions about two particular heat flow maps that exist in the area. One was prepared by the Southern Methodist University Geothermal Laboratory and is widely used. It's the geothermal map of North America. It shows heat flow values ranging on the high end from 68 to 87 milliwatts per meter square, and on the low end down to as low as 34 milliwatts per meter square. There's another map that was produced by the North Dakota Geological Survey that only goes to about 67 milliwatts per meter square with a low of about 39 or so. Well, we had a lot of questions because these maps seem to disagree in certain areas. So we decided to take a deep look and see what's going on with that. And here they are. This is the North Dakota Geological Survey map. One challenging thing about it is that it is based on only three conventional heat flow measurements. And this is where you see we make the measurement of the temperature gradient by logging a deep well. We get information on the thermal conductivity, either from the borehole, from core samples, things like that. And then we just apply Fourier's law of heat conduction and we get heat flow. But again, only 23 sites in the western part of North Dakota in the Williston Basin. Here is the section from the geothermal map of North America that covers pretty much the same area. But here we have 284 sites. I would point out that the average values of heat flow overall, again, large number, small number, heat flow is about 55, heat flow here is about 53. They're pretty much the same. But we've got to ask the question, how do we go about picking which one's the best, and how do we decide which one has errors and which one does not? Uh, well, let's look at how we make a bottom hole temperature measurement and how we apply that to try to get heat flow. This is a typical example. This is from one of the wells in the western part of the state. And what we do is we gather the data, we plot the points as you see here. Then this doesn't show on here, but I'm going to show it on the next slide. And that is we correct for the disequilibrium because we know that the temperature that is at equilibrium with everything in the subsurface around this borehole was disturbed by the process of drilling, particularly by fluids flowing up and down the well. So it's been disturbed. So people make corrections for these things. Well, we calculate a 2-point gradient, and we're assuming in this case the thermal conductivity is 1.76 watts per meter per Kelvin. That happens to be what was assumed in the geothermal map of North America for the mid-continent area. So it's a pretty standard number. In this case, we get a heat flow of about 49. We can do something else. What if we have a whole bunch of bottom hole temperatures close to that borehole? And what I'm showing here is all the bottom hole temperatures within 10 kilometers of this particular well. And the thing you'll notice, if I do a linear least squares fit of all that data at once, I get pretty much the same temperature gradient and very much the same heat flow value. Very interesting thing that occurred. So how do we go about correcting it? Notice I don't put the corrections on here, but let's take a look at what happens if you do. Now I have put on 3 corrections. There's the Keeley correction, the Harrison correction, one that I had developed 20 years ago for the Williston Basin. And you can see where they lie. Here's the original bottom hole temperature. There's the Keeley correction. There's my this blue area is the Harrison correction, and then the Williston Basin correction in here. And you just look at it and say, what are we going to do? They disagree. Which one do I use? Well, one thing about it, all of them were derived in a particular sedimentary basin. And one thing we're learning from all this is that you need to use a correction that was developed in the basin you're actually working with because they don't apply. Now, there's another thing we can do. We can go out and log that borehole when it's at equilibrium and see what we get. Now, here are the gradients. Notice how the heat flow changes overall from 49 to 57 to almost 60 to 64.4. But let's log the borehole. That is the blue line that you see along here. And notice it's not linear. In fact, there are a lot of curves and bounces around in this thing. What does that tell us? The thermal conductivity of the subsurface is not constant. It varies a lot. And you're going to be amazed at how much it varies in the Williston Basin when we get into that. So this is what we've got. And you say, how am I going to deal with this? How am I going to get a good number that I can actually use? Well, in thinking about that, I thought I would share the wisdom of a person who's no longer with us, but has a really good idea. This is my favorite quotation from Mark Twain. I'm asking the question, who get a reliable temperature gradient? Twain says, it ain't what you don't know that gets you in trouble. It's what you know for sure that just ain't so. So let's see how this applies. Here are three maps. The upper two are from the Future of Geothermal Energy, and this is just showing where basins are. We're going to look at four basins and their temperature gradients. So the Williston Basin, the Michigan Basin, the Illinois Basin, and the Denver-Julesburg Basin out here. This map is a segment of the geothermal map of North America, and you get an idea of what the heat flow should be and how the gradients should compare in general. So let's just take a look at the group geothermal gradient plot for each of these basins. A cross section, mostly carbonates in the Illinois Basin. It's located in this lower portion here. Notice what we have is about 16 degrees C per kilometer, surface intercept 20 degrees C, which is about 10 degrees above the mean annual temperature in that region. This is the Michigan Basin. Again, mostly carbonates, Paleozoic rocks. This is a geologic map of the surface. The plot over here, putting all the data. This is over 10,000 data for each one of these things, by the way. The gradient, about the same as we had in the Illinois Basin, 16 degrees C per kilometer. The intercept value a bit lower at 17. This is the Denver-Julesburg Basin off the Front Range of the Rockies. The rocks are the data we're looking at. And the plot over here is from this region, and this data over here is from this region down here. So that's where all the bottom hole temperatures are. Different story in this sense, though. This is mostly Mesozoic rocks, and it's mostly shale and sands. The gradient higher, 23.4. The surface temperature intercept about 20. And then finally, the Williston Basin. The difference with the Williston Basin is it covers all of the Phanerozoic in rocks from the Precambrian into the surface is at the present. The data come largely from this western section of the basin out here. This map goes from the Montana border to the Minnesota border across here. But we're just going to be looking at this western part right here. So now let's do a deep dive into the Williston Basin. It may be unique in this sense. There are 56 formations in the basin in the Paleozoic, and I would say, hey, this is a gold mine for the paleontologist. You got everything from trilobites to T-Rex to go get out there. But if we just go to the upper part, Cenozoic and Mesozoic, accumulated much of about 2,000 meters of shale. It's predominantly shale. The harmonic mean thermal conductivity of this upper section is about 1.8 or 1.18 watts per meter per Kelvin. There are 32 formations in the Paleozoic. Overall, the maximum thickness is about 2,700 meters, It's predominantly carbonate, interbedded with salts, shales, and some sandstones. But now notice that the harmonic mean thermal conductivity is twice that of what we have in the Mesozoic, which means the temperature gradient here is half of what the temperature gradient is there. They're two distinct formations or segments and two distinct gradients. Now, the big thing for us is there are 19 formations that have bottom hole temperature data. And so I can put all of those together and see how they come out. Now, we're very fortunate. Directly across the street from our building is the North Dakota Geological Survey's core and sample library. And I can go over there and get great information, or I can also get it online. This is one of the things, the scout ticket data, which gives me the depth to the formation tops from the Cretaceous to the Cambrian Ordovician unit, the basal unit in the basin for one particular well. Every well has all of this. Not all of them have the same formations. These numbers are all in feet because it's oil and gas in the US. Well, I'm going to go back to this plot we looked at before, where I've made corrections in this sense for the disequilibrium conditions for the Keeley, the Harrison, and the Wilson Basin. And you don't see the Wilson Basin up here. But notice they're linear. I've only made those down to the Madison Formation, or the Mississippian, as we get to it here. And you see the gradients go from 30 to 37.5 to 43.4 and 45.3. But then if I go back to the original log of the system and try to fit a curve to that, what I end up with is a second order polynomial curve. It is calculated this way in this sense. Now, what I'm doing is I'm just taking the heat we think we have in the well. I have the thickness of each formation, and I have the thermal conductivity of the formation. Put in the surface temperature, and then I've got temperature at depth. And that is what these triangles that you see are along here, fitting that curve and going along like so. We have applied this to 250 wells in the basin. We're going to take a look at how they go. But I would like to have you think about this again. The BHT corrections are basin specific. The thermal conductivity varies. You need to look at all of your sections, and the gradient ain't linear. Well, here's how we have approached it. We went to all 284 sites that the geothermal map of North America had, and we looked at all 23 sites that the North Dakota Geological Survey had put together. Over here, we see the calculation for the harmonic mean thermal conductivity and a list of where the harmonic mean thermal conductivities hit as we go from the surface to the Precambrian basement. And you see low conductivity here, higher conductivity there, calculating the systematic harmonic mean thermal conductivity all the way down, you see it increasing. And then we go over here and we apply our what we call T-strat, and it's thermal stratigraphy in a sense. So we take, again, harmonic mean conductivity, the heat flow, the thickness, and the individual conductivities. We plot all of this, and this is what we get for a particular well. I think this one, I'll give you the number in another slide. And then I ran two fits on this. One, this fit is for these T-strat, and this fit is for the bottom hole temperature data. Now, this is uncorrected bottom hole temperature data. Notice these things are almost parallel in here. We started looking at that and said, let's go check all of the North Dakota survey holes. That's 23. And then we started getting this. This is the T-strat curve plotted out. This is the BHT curve. This is for each one. These three wells here were logged by the SMU Geothermal Laboratory back in the 1980s. And then we start going into the North Dakota Geological Survey, and I'm just going to show these 5 in the end, where we're getting the same thing, this sort of semi-parallelism. What we notice from this, if we have the heat flow and we use the T-strat calculation for it, we end up at a depth of about 2,500 meters with a difference between those two curves of about 19 degrees C. We found that this was very good. It was very consistent, plus or minus 3 degrees for the 19 degrees C. And it matches, again, where T-strat matches the conventional heat flow value. And we realized, well, if we turn this around and just go try it on a borehole where we don't have the temperature profile, we could probably come out with what the heat flow is. And we did that. So for 250 wells, there's our average heat flow. This is the standard deviation. Then here are the harmonic mean conductivities again. This is the uh, Paleozoic. This is the Mesozoic. This is the gradient in the Paleozoic. This is the gradient in the Mesozoic. And this is the number of bottom hole temperatures average per well for the 250 wells. And how well did they fit? 0.869. This is a really good fit. But again, all of this is now calibrated against those 23 wells. But I want to look at something else, go back to each one of them, because when Mark McDonald, a former PhD student of mine at the University of North Dakota, who got the North Dakota Geological Survey to drill those, or not drill those, but to go log those existing holes for heat flow, he had a lot of trouble. He did not recognize the bimodal character of the Williston Basin. He tried a number of ways to get things work out. He tried a linear fit of his profile using Fourier's law. He tried Bullard's method. He tried a graphical technique. He used variable gradients. He used different conductivities, and he ended up with something like 7 to 10 different heat flow values for each well. And in the end, he just threw up his hands and says, well, I'll just average them, and that's what I'm going to use. So here's how we applied our T-strat to that. So we went to one of his wells. This is well 1140. We have his temperature log here, and we selected whatever heat flow would make our T-strat calculation match his profile. And so there we have it. Again, this is 19 degrees difference at this point. Now, if we use his heat flow value that he got from averaging those 7 to 10 things, he had a 68.2, and that's what the blue dots are. And notice he has a temperature of 120, where we say, oh, no, the temperature is only about 114 or 112. We went back and checked all of his and found, yes, he had this kind of error in all of them. So we've corrected him. So, oh no, our fit is even better than we had it before. So a quick look at the geothermal map with North America. One thing we found, again, this is 284 sites. We found only 336 that were particularly unsettling, but boy, were they unsettling. Here again is our BHTs, our T-strat calculation, and what our T-strat calculation says if we use the heat flow value from the geothermal map of North America. For this one, it's at 74 milliwatts per meter square. The temperature is over 180 degrees C, but actually the temperature is more like just a bit over 120 or in that region. Well, we've corrected all those, but again, now we have 250. So what I'm going to show you how we went about it, and then how you can do it, and what the results are of doing that. So the first thing, you get the data for the temperature logs. You've got to get the thermal conductivities, all the stratigraphy, so you know as much about the rocks. And you can usually get that from the local geological surveys. Then we created 3 spreadsheets for every well. It was one we called T-strat, one we call the BHT sheet that has all the bottom hole temperature, and then the other is the temperature depth chart. And then we fit the second order polynomials to T-strat and BHT on those. Then we create a master spreadsheet where we have all the data in it, and then we go ahead and carry on with that. So I'm going to show you what we did. Here's the first one. We've already pulled in the BHT data. We've got our thermal conductivity data. We've generated our second order polynomial fits there and there, and we put those into our master spreadsheet. Now this is our T-strat sheet. So again, we're just calculating using this expression. We put in the name of the site. This is something you always want to do. You put in the location, you put in the stratigraphy, the names for everything. And then over here, we're calculating. This is our temperature calculation, but this one in red numbers is the heat flow value we're putting in over here. The depth over here, again, we're just getting the formation top, and you'll notice as you go down, some of these things are the same in a different formation. Why? That formation just simply wasn't there. So you don't change anything, you leave it the same, and the calculation comes out just fine. Now this is at the top. I pulled those numbers over here just to make the plotting easier, but I'm going to jump now to the basement. And one thing I recommend is color all your lines that you need to identify for something specific. And that's what I did. Every one of the bottom temperatures, if it might be the Precambrian, it might be something else like the lodgepole up here, but I give it a specific color because I want to know what it is when I go back. Now I've got almost 300 of these sheets, but I'm only using 250 of them. Okay. And then from that, we go back and we calculate their harmonic mean thermal conductivity. So I go from the Cretaceous to the bottom of the Triassic, over here from the Triassic to the Precambrian, and here from the Precambrian to, or the Cretaceous to the Precambrian. So jumping to the bottom of this, where we cut a lot of things, I'm just going to show you the numbers. That's for this particular well, 1.17 watts per meter per Kelvin. If I go spearfish to the Precambrian, and again, we're cutting out a lot of the top here, 2.31. But then when I do the entire thing, it goes back to 1.56. Obviously, we're mixing the low conductivity stuff and the high conductivity stuff, and that's what you have at the bottom. And again, notice a lot of those things are missing. They're not always all present. And here's how we calculate heat flow. Again, we're looking to get the polynomial fit for T-strat and the polynomial fit for the bottom hole temperatures, and we want it to within 19 plus or minus 3 degrees. Actually, it's even better, just in the 19. So we copy that off the spreadsheet where we have the plot, paste it in here, copy it off here, paste it in there, subtract the two. Now this is fixed. You can't change this. That's what we measured. But you can certainly change one value, the heat flow. So we keep adjusting the heat flow until this difference becomes about 19. And then we've got the heat flow for that well because they fit this condition of here. Now, I thought I would pull out our master sheet, just a little bit of it. A lot of numbers, don't worry about all this. There's obviously not going to be a test, but I just pulled this part out and put it up here again to show you. We're calculating, this is the X value in the equation. So there's my bottom hole temperature fit. There's my P-strap fit. There's the difference. I also include the formation name and the well ID on both sides, just to make sure we get everything together. And again, this thing covers 250 sites. So what have we done with this and where do we go? We've actually now created a new heat flow map that we believe is an accurate guide for the geothermal energy developers. And we've created other spreadsheets that can be used, one for the temperatures, one for the depths, and then we're going to be combining all of that, and we can calculate with the location data what the energy content is of each of those formations. So let's take a look at what that came up to be. Here's our new heat flow map, and I'll point out we have the same cool area over in here, and I'll also point out we have very few holes over here. Why? All the bottom hole temperature data is over here because this is kind of the edge of the Bakken Formation, the greatest producer out there. And there are not enough bottom hole temperatures out here to give us the kind of information we need. So we didn't include them. You see this trend of relatively high heat flow in here. This is underlain by the Trans-Hudson orogenic belt, and I suspect that it's probably due to slightly higher radioactive heat generation in the Trans-Hudson than we have elsewhere. So just a quick look. Again, this is the temperature profile. So I go to each spreadsheet and I pull out the temperature depth all the way down like that, paste it in here horizontally. So now I can pull this into a contouring package and I can contour the Cretaceous, I can contour the Permian, I can contour the Mississippian, all the formations in the Mississippi and so on. And then again, here is the same stuff. All these numbers match up all the way down, all 250 of them. And here's what we've done with it. I have temperature contour maps and depth contour maps for each of the formations. So for a developer, if you just want to do space heating, here's some nice temperatures in the Indian Kara formation. Or we can go down, let's go down to the base of the Madison formation, which is a good bit hotter. And you can see where you would go for that. The Red River Formation, one of the large oil producers in the basin, and we're getting temperatures up into the 160s. And if we go all the way down to the Deadwood Formation, the basal unit, we have temperatures up to close to 170 degrees C. So that's what we've done. And in essence, just to summarize, I would say remember this, the BHT corrections are basin specific. Most basins really only have one or two producing formations. The Williston Basin is really unusual with 19 different ones. So we have this great thing. We can get a good fit. It's just interesting that it came out the way it did. And we have this empirical relationship between the uncorrected bottom hole temperatures and our T-strat. From this, we estimate heat flow. So I would ask you, can you do it in your area? And so with that, I'll just close up the slides and say, thank you very much. And I would be very, very happy to attempt to answer any questions you might have.